This is part 4 of the Earth's Resources topic. It is GCSE AQA Chemistry. It's a dual and triple award topic. Going to recommend that you pause as you go, have a go at each activity. This doesn't really follow on from other areas of the Earth's Resources topic, but it does link back to extraction of metals and the reactivity series and electrolysis. So in this, we're going to look at alternative biological methods of metal extraction, specifically for copper. A few questions for you to try, have a go. So copper is non-renewable. What do we mean by that? It means it's going to run out. It's, in terms of the definitions we've used previously, it is used up faster than it is produced. We've also seen in earlier videos that we are running out of copper ores. Where do the ores actually come from? They all come from the Earth's crust. So it's not very big, it's not very thick, and we are depleting those resources very, very quickly. Because supplies are running short, we're now working to find methods of extracting copper from low-grade copper ores. What do we think this means? Well, you'll remember from previous topics that an ore is something that contains enough metal to be economically worthwhile to extract. So a lower grade copper ore is going to be an ore that has a lower percentage of copper present. The key then is making it financially viable. Couple more questions here and a bit of information. So in copper-rich ores, we have two choices. One, sulfuric acid is added, we react it, and it will make a salt. What salt will it make? Well, sulfuric acid makes sulfates, and copper would make a copper salt, so it's copper sulfate. Once you've made that copper sulfate, we can undergo electrolysis. And method 2, we can do smelting, where we heat the copper ore to a very high temperature, we get impure copper from that, and then we electrolyse to make pure copper. And this is by far the most common method still of copper extraction. So what are the negative impacts of both of these methods? In both of them, we're using electrolysis. That means we've got very high energy costs, very high electricity costs. So that explains the economic impact, but we're also potentially going to be burning fossil fuels to do that. So there is the impact on global warming and greenhouse gases as well. Now that second method, purifying the impure copper, remember we've smelted to get impure copper. This is the diagram. Have a go at the questions that we see here. So what's happening at the positive electrode? And what's happening at the negative electrode, and what would we observe in the reaction? So we're going to start with what we would observe. And that is the mass decreasing of the impure copper anode and the mass increasing of the pure copper cathode. Remember, anode is positive, cathode is negative. We would see copper forming on the negative electrode. And we would see the anode get smaller as copper is oxidised to copper 2. In terms of the equations, at the positive electrode we have copper and it is becoming copper 2. It's been oxidised. We can see that because it has lost electrons. Those copper 2 ions, the positive ions, are attracted to the negative electrode where they get reduced, gaining electrons. So the equation is Cu plus 2 plus 2e minus goes to Cu. So what would happen if I put an iron nail in a solution of copper sulfate? What would we see? Well, after the reaction, we would see the nail coated in copper, we would see the red-brown colour, and we would see the solution lose its blue colour. That's harder to see, but it would be happening even very, very slightly because the copper sulfate blue colour is disappearing because we've got this displacement reaction taking place. And this is the equation for it. Fe is able to kick copper out of copper sulfate. So Fe plus CuSO4 goes to Cu plus Fe SO4. There's an opportunity here for you to have another go at ionic equations if you want to use this as practice. So let's put the state symbols in, and remember, in an ionic equation we break down anything that is aqueous and ionic. So I can break my copper sulfate down into Cu plus 2 and SO42 minus, and my iron sulfate into Fe plus 2 and SO42 minus. I can now get rid of spectators. I've got SO42 minus on both sides of the equation. I then write it out without the spectators. My ionic equation here is Fe plus Cu plus 2 goes to Cu plus Fe plus 2. So let's have a look at what would happen in this electrolysis reaction. We've got copper sulfate, but this time we've got carbon electrodes. Now in this one, we would see copper forming on the negative electrode. The copper 2 ions would be attracted to it, they would be reduced, we would make copper. We would also see effervescence at the positive electrode. So there's a negative ion attracted to it that's then going to be reduced. Oxidized, sorry. So let's have a look at the equations. Well, actually, at the anode, at the positive electrode, it's oxide ions, and they go on to form oxygen, which we have got to remember is diatomic. To do that, I need 2 O2 minus. To then balance the charge, I've got minus 4 on the left, 0 on the right, so I need to add 4 electrons on the right. At the cathode, the negative electrode, my copper 2 ions are reduced to copper 2, and we do that by gaining electrons. Moving on, let's have a look at the equation to show what happens if I add copper oxide to sulfuric acid. So copper oxide, CuO, sulfuric acid, H2SO4. The salt I'm going to make is copper from the copper oxide, sulfate because it's sulfuric, copper sulfate, and an acid plus a base makes a salt and water, so I have my H2O. It is balanced, but I need state symbols: solid, aqueous, aqueous, liquid. Remember, water is liquid. It's not aqueous because that means dissolved in water. We're going to move on and we're going to look at extracting copper from low-grade ores now. And we have to do that because we're running out of higher-grade copper ores. So we need to go for the ones that contain less. The first one we're going to look at is bioleaching. We allow bacteria to feed on the low-grade ore. Through a series of biological and chemical processes, you don't need to know any more than that, we make a solution of copper 2 ions, and we can then extract it by reacting with scrap iron, we saw the details of that earlier, or we can electrolyse it. 20% of all copper extraction now comes from this form, but it's a very slow process. We can get copper from ores that contain less copper, and it is economically viable, but it could take years to do it. So, advantages and disadvantages of this. Advantages: it prevents iron going into landfill. Advantages of scrap iron over electrolysis: it prevents scrap iron going into landfill. Scrap iron has already been used, and we're running out of space here actually, but also it's a far cheaper method because we're not using those huge amounts of energy to make the solution molten so that we can then electrolyse it. What type of reaction do we call it with scrap iron? It's a displacement reaction. Couple more questions. Advantages of bioleaching over traditional extraction method. And it's the fact that it can be used for lower grade ores. But the disadvantage, it's much slower. Remember, it might take years from the beginning of the process to the end. The other alternative is phytomining, and you do need to know the details of this one. So you might get copper left in waste materials that can be left as slag heaps. If we grow plants on the slag heaps that are good at absorbing copper 2 ions, the copper 2 goes into the plants. The plants can then be picked, they can be burned, and then we can react that with sulfuric acid to make copper sulfate solution. So let's look at the questions that go with this. What could I do now I've got the copper sulfate solution? 2 methods to extract the copper. Well, it's exactly the same as bioleaching. I can displace with scrap iron, or I can use electrolysis. And finally, why might the percentage of copper derived from phytomining and bioleaching increase in the future? And it's purely because we don't have the higher grade ores anymore. We are running out of them. So we have to move to the lower grade ores if we're going to continue to maintain a supply of copper. That takes us to the end of this video. Thank you for listening and goodbye.